Hello friends, continuing with applications of Gauss law. Today we take up second application, electric field intensity due to a uniformly charged spherical conducting shell at any point at a distance r dash less than small r less than equal to capital R, where small r is radius of the shell. That is, number one, outside the shell for small r less than r. Second, at the surface of the shell where small r is equal to capital R. Third, inside the shell where r dash is less than small r. So these are three different points where we are to find out electric field intensity due to a uniformly charged spherical conducting shell. So we proceed. For the first case, when point lies outside the shell, that is small r less than capital R. Now we first develop physical situation. A part. Consider a uniformly charged spherical conducting shell of radius r having surface charge density sigma such that total charge on the shell be, say, q equal to 4 pi r square into sigma. Let us mark it as equation 1. So you can look into the diagram. There is a spherical conducting shell which is uniformly charged, having surface charge density sigma and of radius r. Okay. Now B. Let P be any point outside the shell at a distance capital R from the center of the shell where electric field intensity due to the shell is to be determined. Now C. Assume a Gaussian surface. Now assume a Gaussian surface S in the form of a sphere of radius capital R with center coinciding with the center of the shell such that point P lies on the surface of the Gaussian sphere as shown in diagram. Now next step is D. Charge enclosed by Gaussian surface. We have to calculate. The charge enclosed by the Gaussian surface is Q. Say Q. It is equal to 4 pi r square into sigma. E. Electric flux linked with Gaussian surface. Now in the fifth step we have to calculate electric flux linked with Gaussian surface. Let us see how much it would be. Now, since electric field intensity at every point on the surface of Gaussian sphere would be same, say E equal to k naught q by r square along radius directed outward due to symmetry. Therefore, electric flux linked with whole Gaussian surface would be, say, phi E equal to E dot S, or it is equal to mod E mod S cos theta. But theta between area vector S and field vector E is 0. Therefore, electric flux phi E is equal to E into S, or it is equal to E into 4 pi r square. Let us mark it as equation 1. F. According to Gauss law, phi E must be equal to 1 by epsilon 0 times q, the charge enclosed. Therefore, E into 4 pi r square is equal to 1 by epsilon 0 times q. Let us mark it as equation 2. G. Now E is equal to q by 4 pi epsilon 0 r square, or it is equal to k naught q by r square. So we write the expression finally E is equal to k naught q by r square. Discussion. Number 1, the expression E is equal to K naught Q by R square reveals that this is the electric field due to a point electric charge Q at a distance R from it. It means whole of the charge on the shell can be assumed to be concentrated at the center of the shell. So remember this result. This result is going to help you while dealing with numerical problems. Now second, electric field intensity in terms of surface charge density of shell we are to calculate. Now substituting the value of Q from equation 1 in equation 2, we get E is equal to K naught 4 pi R square sigma by R square, or we can write E is equal to 4 pi R square sigma divided by 4 pi epsilon 0 capital R square, where 1 by 4 pi epsilon 0 is written in place of K naught, because K naught is equal to 1 by 4 pi epsilon 0. Now here 4 pi cancels, and then we are left with R small r square into sigma divided by capital R square into epsilon 0. Or we can write finally E is equal to small r square by capital R square into sigma by epsilon naught. So this is the electric field intensity at any point at a distance capital R from the center of the shell of radius small r, having surface charge density sigma. Okay. Now we take up second case of the article, electric field intensity at any point on the surface of uniformly charged shell. Now proceeding with the previous part of this article, if point P lies on the surface of the shell, then capital R will be equal to small r, that is radius of Gaussian sphere will become equal to radius of uniformly charged spherical conducting shell. Therefore the expression E is equal to small r square sigma divided by capital R square sigma R square epsilon naught can be replaced by capital R square sigma divided by capital R square epsilon naught. R square cancels, then we are left with sigma by epsilon naught. Therefore E will be equal to sigma by epsilon naught, and direction is perpendicular to the surface. Now we come to the third case, where we find electric field intensity due to a uniformly charged spherical conducting shell at any point inside the shell. And again we have to follow the 7 steps to deal with Gauss theorem. So A, consider a uniformly charged spherical conducting shell of radius r having surface charge density sigma, such that total charge on the shell be, say, Q equal to 4 pi r square into sigma. Let us mark it as equation 1. B, let P be any point inside the shell at a distance r dash from the center of the shell where electric field intensity due to the shell is to be determined. C, assume a Gaussian surface S in the form of a sphere of radius r dash with center coinciding with the center of the shell, such that the point P lies on the surface of Gaussian sphere as shown. D, charge enclosed by Gaussian surface, say Q is equal to 0. E, electric flux linked with the Gaussian surface. If at all there is any electric field, it would be same at every point on the Gaussian surface and along the radius directed outward due to symmetry. Therefore electric flux linked with Gaussian surface S, say phi E is equal to E dot S, or it is equal to mod E mod S cos theta. But theta between electric field vector E and area vector S is 0. Therefore electric flux phi E is equal to E into S, or it is equal to E into 4 pi r dash square. F. According to Gauss law, phi is equal to Q by epsilon naught. But charge enclosed by Gaussian sphere is 0. Therefore, E into 4 pi r dash square is equal to 0 by epsilon naught, or it is equal to 0. And finally, G, where we find E is equal to 0. Hence, electric field intensity inside a hollow spherical conducting shell is always 0, and it acts as a shield from external electric field. Now, it could be any hollow conductor, maybe spherical, maybe cylindrical. So, electric field intensity inside a hollow conductor is always 0, and it acts as a shield from external electric field. That's why signal carrying wires are always shielded to avoid deformation of information contained in the signal. For example, TV cable. You look at the diagram. Here we have signal carrying wire, and this is polythene cover to keep wire at center, and this is shield, and this is PVC protection layer. So this is how cable, computer cables, TV cables are manufactured and prepared. The aluminium foil on the wire, it is a cylindrical conductor which is hollow from inside, so field inside will be 0, because inside there is a signal carrying wire. So the signal is protected from outside or external electric fields. Assignment 1.5 continued. Question number 17. Derive an expression for the electric field intensity due to a uniformly charged spherical conducting shell of radius r having surface charge density sigma at any point P at a distance r from the center of the shell for number 1 r greater than r, that is outside the shell, and prove that whole of the charge on the shell is concentrated at the center of the shell. Second, r equal to r at the surface of the shell. Third, r less than r, that is inside the shell, and prove that a conducting shell can be used as an electric shield for the wires carrying signals having information. The question number 18. Calculate electric field intensity due to a uniformly charged ring of radius a and width b having surface charge density sigma at any point outside the ring, on the surface of the ring, inside the ring. Question number 19. Calculate electric field intensity due to a uniformly charged solid sphere having volume charge density rho at any point outside the sphere, on the surface of the sphere, inside the sphere. Question number 20. An atom was earlier assumed to be a sphere of radius a having a positively charged nucleus of charge plus Ze at its center. The nucleus was believed to be surrounded by a uniform charge density of negative charge that made the atom neutral as a whole. Use Gauss law to find the electric field of this atom at a distance r less than a from the center of the atom. Okay, so these are some questions on this application, and you are supposed to solve them. Okay, so here we finish with this second application of Gauss law. Tomorrow we will take up next third application of Gauss law, where we will study electric field due to a uniformly charged thin infinite rod at a distance r from it. Till then, goodbye. Thank you. God bless you.